Okay, so now, really importantly, one of the big things that we want to do is determine essentially how good is this redox reaction that's taking place. How good is my battery going to be? How well have I set up this galvanic cell? And so essentially, you're going to start seeing this E naught symbol, which is your standard cell voltage, and it's just a measure essentially of what's called the electromotive force, or how strongly those electrons are forced through the wire, if you will. And sort of talk about what the standard cell voltage tells us, but know that the standard cell voltage is essentially set up based on a comparison to the standard hydrogen electrode, which is given a value of 0.00 volts. And that's just sort of our standard reference, and then everything else is just based off of a comparison to that standard hydrogen electrode. You used to be provided with a chart on the AP chemistry exam. They no longer give you the chart. Don't freak out. It's actually a little bit easier. They now specifically give you the reduction potentials that you need. So instead of having to scan through an entire list, they just give you the reduction potentials that you need. But as you look at one of those charts, or if you look at the reduction potentials that you're given in a problem, the more positive the value is, the more likely it is to be reduced, in comparison to that hydrogen electrode, which is, again, what the standard was. Anything that is, of course, less than that or negative is going to indicate something that is less likely to be reduced. And so here's an example of a standard reduction potential chart. Again, keep in mind, these are going to list out for you the reduction potentials. So as you look at this here at the top, these things here at the top are really, really, really strong oxidizing agents, aka they're very easily reduced. And as you look at their reduction potential, we have a really positive reduction potential, indicating that they're very easily reduced, or they're really strong oxidizing agents. As you move down that list, though, note we get to our standard hydrogen electrode of 0.00, and then you get these even negative reduction potentials. And so as you move down, the further down that list you go, note that things like the lithium ion, these things are not going to gain electrons very easily. And so as you see, their reduction potentials are very, very low. And again, that's just sort of a quick interpretation of the chart. You will no longer be provided this giant chart, although it will be probably a pretty good reference as you're working through some homework problems. I like to use it. It just gives me a good frame of reference to some of the other things that we may be working with. We're going to then use that chart, or the ones that are provided to us in the problems, to calculate what the standard cell voltage is for a galvanic cell. And this is one of the big things that you'll have to do. It can seem a little daunting right now, but it's pretty straightforward. All you have to do is take a look at the reduction potential, or the standard cell voltage for the reduction half reaction, add it to the standard cell voltage for the oxidation half reaction. Just keep in mind that the chart that you're given, and oftentimes what you're provided in the problems, are simply reduction potentials. And so in order to get the oxidation, or the standard cell voltage for the oxidation half reaction, you just have to reverse the sign. It'll have the same magnitude, just opposite sign, for the oxidized species. And we'll take a look at that. Don't freak out. So again, these are reduction potentials. So if you're talking about something that's being oxidized, you have to flip the reaction and then also flip your sign. And we'll talk about it. Here's a quick example where you're given a redox reaction and then you're given two reduction half reactions. So this is very, very similar to the type that you will get on an AP question, where instead of having to reference a chart, you're just given the things that you need to answer the question. Some things to sort of keep in mind as you check this out. Again, the more positive the standard cell voltage is, the more likely that thing will be reduced. And so as you look at this, the copper 2 ion is more likely to be reduced than the zinc ion will be. And again, we can just determine that by recognizing that this is more positive than this one is. So when you're trying to determine what the standard cell voltage is for this entire galvanic cell, all you have to do is flip the sign of the thing that is being oxidized. It's going to have the same magnitude, it's just going to have the opposite sign as what's given to you in the reduction potential. So again, as you look sort of at this equation, you can tell pretty easily that the copper 2 ion is gaining electrons. So its reduction potential is going to be plus 0.034. But then zinc, you should be able to tell here, is losing electrons. We go from solid zinc to the zinc ion, so we're losing electrons. And because this is the reduction potential, again, we just have to flip the sign to get what the standard cell voltage of the oxidation half reaction is. Which is why we end up down here with the plus 0.34 plus the positive 0.76. And we'll work through lots of examples to get you really comfortable with that. Okay, and then ultimately for a voltaic cell or galvanic cell, we want to have a positive standard cell voltage value. It just indicates then that the reaction is actually going to happen spontaneously. It will be thermodynamically favored. Again, thermodynamically favored is going to be the key terminology to use, but recognize spontaneous is also a good way to sort of frame it in your mind, and that's the way I've always thought of it. So it's tricky for me as well to reframe it as thermodynamically favored, but try and use that terminology. It'll just help you out in the long run. I think it'll make more sense once we get to the thermodynamics unit. But you're looking for positive standard cell voltage values. If you don't then have a positive standard cell voltage value, the reaction is not going to happen. It'll make a really bad battery. Okay, and then last sort of thing here to keep in mind is you can relate the standard cell voltage, or that E0 value, to what's called Gibbs free energy. We'll talk again a lot more about Gibbs free energy as we move through the next couple of units here. But for right now, we really don't need to know too much about it other than, what the sign of the Gibbs free energy tells me, and then we'll come back and sort of reinforce Gibbs free energy once we hit through that thermodynamics unit. But essentially, there's a formula that you're provided with that relates those two values. You've got the number of moles and what the Faraday's constant is, which we'll talk more about. But basically, and this is pretty straightforward if you understand your algebra, if your standard cell voltage is negative, so if this is negative, because how the equation is set up, if you're multiplying a negative times a negative, you'll get a positive delta G value, or a positive Gibbs free energy value. And just know at this point that a positive delta G value is not favored, or that reaction is not going to happen spontaneously if you have a positive delta G value. On the other hand, if you do have a positive standard cell voltage value, so if this is positive, again, based on how the equation is set up, a negative times a positive, you're going to get a negative Gibbs free energy value. And that is thermodynamically favored, or that is going to indicate some spontaneity to your reaction. As you're trying to figure this out or sort of keep this straight in your mind, at this point, all I want you to think about is, okay, Gibbs free energy is going to tell me whether or not the reaction as written is spontaneous or not, whether it's thermodynamically favored or not. And if you have a negative delta G, if you have a negative Gibbs free energy, think of it as sort of you got to spend that money to make things happen. And when you're spending those dollar bills, what's going to happen to your account balance? But it's going to go negative. And so sort of frame it like that. That's how I think about sort of spending money. Your balance is going to go down, but you've got to spend that money in order to make things happen. And so a negative delta G indicates a thermodynamically favored reaction, something that is spontaneous, that will happen on its own.